Hi, my name is Bob Grinier and I'm a volunteer with the Martin Fleischmann Memorial Project. Thank you for joining me this evening as I give you an update to the project to put a proposal forward to try and clean up the triated water at Fukushima Daiichi nuclear power station. So first off, unfortunately some bad news. Stephen, who is helping us with the application, he unfortunately has some family problems and health-wise, and this is often the case sometimes when you get retiree or near retiree volunteers that we don't last forever, and so I wish him and his family well, but that hasn't stopped the rest of us moving forward. And I'm going to talk a couple of things. One is the paper, which I've given a link to in the discussion of this live stream. So if you go to the live stream, there's a link to this paper, which Slobodan Stankovic dug out. And I think it's a very good working document, and we're going to go through that. And also, we went to Vietnam, or rather we didn't go to Vietnam. We went to look for this type of really ultra pure calcium carbonate that they have in the southern part of Vietnam. And you may have had some wall paint or some white plastic or some toothpaste, or you might have had some pills, for instance, that would have had calcium carbonate from this or a similar source. And so here is the place. It's I'm probably going to get this very wrong, and my wife will be very upset about that. But it's Hong Ti Fat Chin Soi. I've probably got that completely wrong. But anyway, they have this huge quarry of very high purity calcium carbonate. And if I zoom in here, you can see that the calcium carbonate content is 98.76. A little bit of iron oxide in there, a type of iron oxide, magnesium carbonate, and some very small quantities of everything else. So, and moisture actually is a reasonable chunk of the actual remaining amount. So one presumes that is H2O. Now, the thing about burning a Marsa gas is that when you want to create limelight, and the Marsa gas and HHO and water gases generally will do this same limelight effect, you need to heat up the calcium carbonate to drive off CO2 so that you end up with Ca and CaO, calcium oxide. And the interesting thing is, if you remember from our Marsa gas testing, when you had a Marsa gas itself, when we were looking at it with bolometer, it has a low temperature, at least as far as the bolometer is concerned, and Slobodan Stankovic and other authors have shown that this is in the range of about 100 and 135 degrees centigrade. When that is exposed to a metal without any additive, it tends not to get anywhere close to the so-called melting point of the metal before there is some interaction, and I believe that I have demonstrated that the interactions aren't necessarily melting, but it would appear that there is some sort of transmutation going on, and we've observed that in indium, in copper, zinc with the 10-yen coin, and with tungsten and with titanium. And so something different is going on. Now, if you add some type of carbon containing additive, the carbon interacts with it in a different way, such that you actually get a higher temperature recorded on the bolometer. So if you remember, when we used gas that was containing, I think it was maybe it was methane or ethane, ethanol or something, some hydrocarbon or carbohydrate, I think it was hydrocarbon in there, but something containing carbon. It in theory, it lowers the temperature, is kind of what the kind of marketing is, but it actually, when you observe what it does to, for instance, titanium plate or other materials, the actual temperature recorded on the bolometer was higher. And interestingly, you didn't see this incredible incandescence. But what you did see is no melting. The melting was much harder to achieve. Even though the recorded bolometer temperature was higher, there was no melting. And I believe this is to do with the coherence and possibly driven by the oxygen and the hydrogen, the OH group, the hydroxy group, self-mazing and forming coherent matter. And also in part because, as I argued in the previous presentation, oxygen is a paramagnetic element, very, very special paramagnetic element. And I believe that in the Marsa gas vibrator and electrolysis system that there are we observe strange radiation tracks, therefore implying that these kind of things are potentially these magnetic structures are forming, and that these may be binding to the paramagnetic oxygen, forming these clusters, and when you burn it you get something coming out which is akin to an exotic vacuum object. So there's a couple of pathways there, and I think the carbon kind of interrupts that, and it becomes something that the gas is preferentially interacting with rather than being able to maze quite so easily. Anyway, that's the hypothesis. So my view is that when you would apply HHO or good water gas like a Marsa gas to calcium carbonate, it would interact with the carbon in the calcium carbonate and cause the increase in real temperature such that it would drive off the carbon dioxide, and you would end up with the calcium oxide that you need in order to do your limelight. And at that point, you would start potentially producing this coherent matter, which is what we want to deal with the radioactive materials. So, so that is that. And so we contacted this company, and fortunately, the advantage of having a Vietnamese-speaking wife. So thank you very much to Kim for arranging this over the last week. And she worked with some people she knows in Vietnam, and they came up and within a day they sent us a 10 by 10 by 10 centimeter block of this quarried material, and you can see it's really rather beautiful. I mean, it's very consistent in grade. And this is the link to the site I've just given you there. There's a bit.ly shortened link there for those where that works. It doesn't necessarily work in all countries. And so because this weighs a fair amount, I asked them to take a section of it, and we have a 2 centimeter section by 10 centimeters by 10 centimeters coming to us for a test. Now, I have another bit of bad news, is that I really don't think it's going to be possible in time to get to America because of the cold that's been going about. And so that is still out there, but as a fallback option, I'm looking to go to Slobodan Stankovic in Switzerland, and I have been informed that this sample here should be with me in about 13 days. So I will have that before I would need to be going to visit Slobodan. And what we can then do is we can take a sample of this before and run several tests on it using his HHO generator and see what we get out of it. And tomorrow morning I will be meeting SciTech up the road to look at doing some SEM imagery and EDS on a large platform device, and with the Vega Valley. And I'm also going to be discussing either getting this looked at once I have done the testing, but at the same time we'll send samples to Alan as well, just in case SciTech are unreliable in terms of getting the testing done. So we've got a fallback option, and what I'm proposing actually is I've got some deuterium, and we'll run some tests by electrolyzing light water, and then we'll run some tests by electrolyzing for the same period and exposing the gas for the same period using the deuterium enhanced water. And if if you look at the Parkhomov reaction tables, typically a reaction that involves protium, one hydrogen, if that produces a transmutation, then it's more likely that the transmutation will occur with deuterium. And if you have tritium, then one can infer, and in fact this is the claim of Dr. Royshin Amaza, that when you use tritium, the level of transmutation is much faster. And if you looked at Edmund Storm's ICCF 23 presentation, he's saying that with the use of hydrogen in his reactor, he did see some excess heat, but it was not at the level of when you are using deuterium. So there is a pattern here. And why is that? Well, firstly, you get more energy out, and if this feeds back into the overall process as a kind of like positive feedback loop, you can imagine that excites the coherent matter, and then that can work faster. The other thing is that actually deuterium is a boson, so it might be easier to get in there. So there are ways and means, but I would expect this pattern to happen, and certainly the evidence by Dr. Royshin Amaza, his claims are that this is the case. And so that even without access to tritium, we might be able to show potentially that there is a higher production of either heavier isotopes of calcium or a higher production of potassium coming out of the system. I need to run the reaction tables and find out essentially what we might expect, and see if we do see that having done an equivalent exposure but with the deuterated gas. So that is about as far as we can take it with that. And I would propose just impinging the gas directly onto the surface, but also, if you recall, we were able to create this, or rather Slobodan Stankovic was able to create, by passing through a carbon capillary, he was able to create this kind of like a beam, like a maser beam, a coherent matter beam. And it might actually be the case that if we drill some holes through this, and it depends how brittle it is, but if we can drill some holes through this, we may find we get enhanced transmutation because of this shearing and toroidal and poloidal forcing that goes on when you pass a gas through, at a slightly offset angle, a capillary. We might end up by forcing the function of producing toroids, which would then pinch down and accelerate the transmutation process. So sort of like the capillary discharges done in Russia that I've discussed a number of times by Anatoly Klimov. Okay, so there's a couple of options which we can use with this, and this may not be the solution, but I think we have to give it a try. Now, what we're going to do now is we are going to look at the paper that I've given the link for. So has everyone got it? Has everyone got the paper? Anyone got the paper to look at? Anyway, you'll see it on my screen. So so this is the site, and this is the paper. So the link that I sent everyone is up here. If I get rid of my mugshot. So there we go. And I have put some notes on it here. So it was actually published online on the 12th of May 2020. So it's just over a year old, being in the public domain. And it's called Discussions on Triated Water Treatment for Fukushima Daiichi Nuclear Power Station. And these are the authors, and Slobodan has actually tracked down contact details for some of these. So I think once we've got a good proposal together, we should probably contact these people directly. And so I'm just going to read a few things. You can read along with me. So, a series of discussions on triated water of the Fukushima Daiichi nuclear power station, FDNPS, was carried out. A large amount of contaminated water has been generated in the Fukushima Daiichi nuclear power station, which we're going to refer to as FDNPS from now on. Radioisotopes in the contaminated water have been removed except tritium, and thus triated water has been left and stored. As of March 2019, 1.1265 million tonnes of triated water has been stored in tanks. The average tritium concentration in the triated water is 1,000 becquerels per centimetre cubed. Various options for handling the triated water, such as discharge into the sea, geosphere injection, underground burial, and vapor or hydrogen release. It's interesting, I kind of hypothesized that hydrogen release would be a good method, and we'll talk about that and why I believe that that is probably vastly more superior to many of the other ones in balance. Release with and without pre-treatment were discussed on the basis that there is no scientific impact on people. Now that is an interesting phrase, where were discussed on the basis that there is no scientific impact on people. What is that kind of suggesting? Well, it suggests to me that basically if you're exposed to what the process would result in exposing you to, it's not going to change in any meaningful sense during your lifetime the chances of you suffering some ill effect from the level of exposure that you get exposed to. So there's nothing that could be measured scientifically, i.e. there would be no p-value that's low enough to say that this person got cancer. And this is a way that these things are justified and explained, and it might be that maybe 100 people in the world or an extra 1,000 people in the world get cancer, and you would never be able to attribute the straw that broke the camel's back to the fact that a process was used to get rid of this triated water. It may be that no one gets affected, but you could never prove that it was as due to this release. So I think that's kind of what they're suggesting in this no scientific impact on people. Of course, there are other things in the planet, like fish and things, which could be an issue. But fish don't tend to revolt and have petitions and unelect people, do they? So through the discussions, 11 options for handling triated water were summarized. At the same time, some experimental tests of tritium separation with small-scale and or full-scale component test stands were also carried out. As a result, it was concluded that the tested separation technologies could not yet be applied to the case of the FDNPS. No selection from the 11 options has yet been recommended, and further discussions for triated water have continued with public hearings. Yeah, possibly with the Tesla turbines. So get your thinking caps on. All of them are good things to consider. So the introduction. The decommissioning of the Fukushima Daiichi nuclear power station is long-term hard work, 30 to 40 years. I would suggest that in any of these events, that if they estimate it's going to be 30 to 40 years, it's probably going to be 40 plus years. So this is a couple of generation thing, really, at least. And we still talk about Chernobyl, and it's a big problem, Chernobyl, still. And so I'm not sure that this is reasonable. I think maybe this is the first stage in their decommissioning. It says here, all the radioisotopes except tritium in the contaminated water can be removed by the Advanced Liquid Processing System, ALPS, based on an adsorption process. However, it is clearly understood that it is difficult to remove tritium in the contaminated water. For this reason, the Triated Water Task Force was established in December 2013 in the Cabinet Office of Japan. These options basically consist of final disposal methods such as discharge into the sea, geosphere injection, underground burial, and vapor or hydrogen release. The combination with pre-treatment such as dilution and isotope separation has been discussed. So In certain cases, you don't need to do the isotope separation, so it's cheaper. And in some other cases, you have to dilute whatever it is in the means that you are discharging it in order to keep below legal limits. Not limits of any type, but legal limits. You're not getting rid of it, you're just releasing it at a rate that it has no scientific impact on people. Okay. All cases were examined on the basis that there was no scientific impact on people. Okay, all right. So triated water in the Fukushima Daiichi nuclear power station. Generation of contaminated water. Basically, the water drawn from the... Okay, so they have this process where they have to cool the melted cores, and this produces an amount of triated water. Now, that doesn't change, actually. They just keep cycling the coolant water around. What happens is you get groundwater that comes in, and this adds to the amount of water in the reactor. And so what they have to do is they have to drain some of that out, and after treatment, they put that into storage. And you've also got some rain that comes in here. And what they have actually is they initially put a seaside steel wall in here, an impermeable steel wall at this side, and then they put these series of frozen walls in here. And what they do is they actually, from the sub-drain of this groundwater, I guess they're trying to keep the groundwater low or whatever, they actually take some water out from here, and that goes actually, as far as I understand it, directly into the sea. It says the water drawn from the sub-drain is discharged into the sea after confirming that the radioactive concentration, including tritium, i.e. it's not just tritium, is less than the limit value, i.e. the level at which we're not going to get into trouble for discharging it into the sea. Thanks to these measures, the increasing rate of contaminated water was decreased from about 540 meters cubed to about 220 meters cubed, average full year 2017. So now you understand why they had this requirement of between 50 and 200 or 300 or something in the call for ideas. So at this point in full year 2017, it was 220 meters cubed per day. So it says here a target increasing rate is set to be less than 150 meters cubed per day until 2020. So I actually think it's actually lower than that now. Lower than 150 meters cubed. So, but if we were to assume it's 150 meters cubed, then those sort of 15 megawatt figures that we were looking at for the electrolysis part of the process alone, without any energy recovery, would look like about 45 megawatt with a Mars vibrator electrolysis systems. Okay, so contaminated water treatment. The contaminated water is processed by three systems: a cesium absorption system, a desalination system, and the ALPS. The contaminated water is first processed by the cesium absorption system, and a major part of the cesium isotopes is removed from the water. Cesium is really, really nasty. It has a half-life of about 30.6 years, something like that, and it replaces salts in your body, which we're a saltwater creature inside our body, not outside, but inside. And this means that you then have something in your body that is continuously emitting gamma rays throughout, essentially, your life. And so it's extremely unpleasant. And because it's kind of like cesium and strontium, they are some of the most significant fission products, and they're both beta isotopes, and so they come either side. Like if you take uranium-235 and you split it in half, there's two peaks either side, and like one's cesium, one's strontium, and so on. So they're a large proportion of the fissile products. So you need to get rid of the cesium, absolutely. The water is then sent to a desalination system using the reverse osmosis membrane. This is kind of like often what they use to create, so-called drinking water, when it's not mineral water. The permeate water from the desalination system is recycled as cooling water of the reactors. As the amount of contaminated water increases, the increased amount of water must be removed from the recycled stream and stored. For this purpose, ALPS has been developed, constructed and started operation in 2013. ALPS is composed of several absorption units, and you can see a little image here. And it's blah, blah, blah. Essentially, you can go and read this in your own time, and it's talking about getting rid of the cesium. The point that I've got down here is define low, because down here it's saying that the desalination system does not function as a removal system of radioisotope. ALPS can remove radioisotopes, except tritium, to quite low levels. To quite low levels. At the start of the document, it's saying it completely removes, or essentially it's implying that it's completely removing these isotopes. And here it's saying it removes it to quite low levels, okay? And what does that mean? Well, here is the chart. And as you can see, the adsorption system, the desalination systems, and the outlet of the ALPS, the tritium level does not change. So this is a logarithmic scale here, becquerels per centimeters cubed, and you can see that the cesium 134, 137, the radioactive isotopes of cesium, and the strontium 90 isotopes actually are significantly more levels of becquerels than the tritium content. And in fact, if you add those three together, it's like, bordering on 4 times the level of radioactivity of the residual tritium. So you definitely want to get rid of these things. And you can see as you go across, you get a reduction from these. So this is the inlet, this is the outlet of the cesium, and I don't really see so much change going in here, but what it's basically doing here is it's getting rid of the salt, like sodium chloride and potassium chloride, one would imagine, from the water. So there's no real change in the level of radioactive isotopes here. Now, it is 10 to the minus 4 down here, and so this is 10 to the minus 4, 10 to the minus 3. There is some cesium, strontium in the residual triated water. Yes, granted, it is very much lower, but if you add those 3 peaks up, it's getting on to 10 to the minus 3, which is it is a percentage of the becquerels per centimeter cube. Now, the thing is that if you were to electrolyze this, one would imagine that this would build up in the electrolyzer. So it would concentrate, and that's not necessarily a bad thing, because you could then wash it through once in a while and run it through the same system again, and you'd be back down to these low levels. So you can actually recycle that water and deal and capture those radioactive isotopes, rather than the vapor release system, which will actually dump those into the environment, or the dumping it into the sea, which would dump these into the environment. Okay, so you would actually progressively remove those. And so that's kind of my point there, and it's just showing the half-life here from the event and the level of triated water, because it's actually arguing here that there is actually no more tritium in the reactor than started with, and so you're kind of like, as you process it, you're getting less and less. Not just because of the decay, but because no more is actually being synthesized. I'm not quite sure about that, but anyway, that's what it says. Okay, so the increasing rate for triated water is 55,000 to 80,000 meters cubed per year, and I calculated that is actually the 220 meters per cube per day, and I think that is below that. I think it's below this figure that they are targeting of 150 meters per cube per day. So. But even at that level, we're going to need 45 megawatts to do the electrolyzing in theory. So it's doable. Okay. So and that it says the average tritium concentration is 1,000 becquerels per centimeter cubed, and the total amount of tritium is 10 to the 15 becquerels, approximately 3 grays. I think that is 3 grays. It's another measurement unit for radiation. Okay. So. I think it is, maybe. I don't know. I might be wrong. The discussions on triated water treatment, and so they have these various methods. It is also a significant point that the technology has been proven. So whatever technology is proposed has to have been proven and is well understood in Japan. Well, we could probably do this is well understood in Japan because, at least by a few people, by Matsumoto and by Roishi Namasa, and proven, well, I think that we've proven it does transmutation. And does it do transmutation of beta isotopes? Well, one would expect it does. And actually with the cesium in the vibration system, we saw transmutation. I published that data at ICCF 22, and I'll probably explore that in the lead up to making a proposal here. But I do think that it has been proven to deal with cobalt 60, which is a beta gamma isotope, and therefore by Yule Brown in 1992. And there are testimonies that there are videos of that is the case. So I think it has been proven. And I think the overall family of technology is well understood by, I don't know what that means, well understood. Does it mean like the general public understand it? No, it can't possibly be that. It has to be that there are parties that are Japanese that understand well that the process can do what it claims to do, okay? I mean, obviously, if you're talking about electrolyzing water, then there's going to be vast numbers of people that know that water can be electrolyzed. If you are talking about putting material into concrete or burying it under the water or throwing steam into the environment or dumping it into the sea, then I think most people can actually understand that. So yeah, it is an area which it's kind of like we've put this situation in here. It's going to make you difficult to comply with the terms, but anyway, such that it is. I think that if we could get to do a test with the triated water, it'll either do it or it won't, and then it's a completely different option to the ones that you're seeing here. Anyway, moving on. Through the above discussions, 11 options were first chosen as the final disposal methods, and these options were finally summarized into 5 options by combining with and without pre-treatment, such as dilution and isotopic separation. The following are summarized options: geosphere injection, no pre-treatment, post-dilution, post-separation; discharge into the sea, post-dilution and post-separation; vapor release, no pre-treatment, post-dilution, post-separation; hydrogen release, no pre-treatment, post-separation; and underground burial with no pre-treatment. And then they go on to say that they've got 0.8 million cubed. That was at 2015. We know it's 1.25 million tons now. Their flow rate's 400 meters cubed a day. We now know it's under probably 100, definitely under 150. Tritium concentration is between this and this, but the average rate we understand is about 1,000. Separation factor. Now, in their call for suggestions, the separation factor was that they had established was a 10 to 1 separation. They want a separation factor of greater than 100. Okay. And in this call, but in the call that we are referring to, they want a separation factor of greater than 1,000. Well, it would be great if you could just get rid of it, wouldn't it? I mean, that's obviously the thing that you want to target for. So if we can achieve greater than 100, then that's good. So the amounts of secondary waste, and in fact, this means you're getting 1% out. And that is actually quite close to what Yule Brown did with various radioactive isotopes. Now, granted, he was doing it with aluminium and iron and building up the coherent matter as I see it, and the ball lightning causes this matter collapse, and you just end up with carbon, as observed by many authors, including ourselves. But that would be very close to the separation factor, and if you just did it twice, then then you would be getting very close to the 1/1000 or more, as I calculated in the previous presentation. So the amounts of secondary waste and radiation exposure of workers is also taken into account. So yeah, you don't want to get people near this stuff. So you really want to have a system that is autonomous. It runs by itself and very low maintenance, and that is one of the advantages of the Amasa vibrator plates, because whilst and in fact, you'll see when they're discussing here about electrolysis, they said that the electrolyzers tend to lose their efficiency quite quickly. The thing about the Amasa vibrator plates, yes, it might be 57% efficient, but it's very robust because your plates are not so close together, and the chances of things getting stuck to it are very slim because they're shaking up and down. They're knocking away everything that might fur them up, and so they're quite resilient. So would you rather have something that produces 70% efficiency but dies after 10 days, or something that runs for 6 months before you need to swap some plates out? Let's say these are arbitrary figures, but it runs at 57% efficiency. So you're gaining maybe, I don't know, 40-50% on the efficiency, but you're having to swap it out every few weeks or week or every 10 days or something. So I'd rather go for the efficiency. And you also have got the potential for the more oxygenation, the better quality gas being produced that may do more levels of transmutation, and also the vibration itself may pre-remediate the material and that is being processed. Okay, so the first here is geosphere injection. For the case of no pretreatment, and no pretreatment option is assumed to be an option because a legally permitted concentration for geosphere injection has not been established there. So I'm pointing to this one here. So what they're saying is, what geosphere injection is, you put it underground and you don't pre-treat it because you don't worry about the cesium isotopes because it's underground. You can't see it. It's not going into the ocean, it's not going into the atmosphere, it's underground, that's going to be buried. That's the idea. And but you don't need to pre-treat it because no one's done it to this level before, and no one's had an accident to say, well, following the accident all of the material came up and it caused problems in the groundwater, it caused problems with the food chain, and so there's no standard, so we'll be defining the standard. So it's kind of a little bit, this, you've got to be practical about this. The problem does have to be solved, but this little bit grates on me. The treated water is sent by injection pump and is injected deep underground into a deep underground reservoir. And so basically they have a map here to just look at it with a visual. So they have a sandstone reservoir, and then on the top they have something that would shield it, like a mudstone, so that the material would not come up. You would have it some 2.5 kilometers underground, and you would have an ability to sample it from period of time to check, that it's doesn't look like it's leaking, or it's, The problem is you actually have to find a site that complies. Like it's sealed, it's a zone, it has everything you need underneath and everything you need on top. And so on. So, first you've got to find a site that's suitable and so forth. So, the technology of geosphere injection has been developed for carbon or carbon dioxide capture and storage. So, yes, it has been proposed and even developed, that is to say, actually exists for carbon dioxide capture and storage. So, this is a known technology. However, a suitable geosphere layer must be found. A suitable method for long-term monitoring of deep geosphere layers should also be developed. And the reason is because you're not getting rid of the tritium, the cesium isotopes and the strontium isotopes. So they've got a much longer isotope half-life than the tritium, and much more biologically difficult to deal with. The discharge in the sea is obviously their preferred option, and you can see it by the level of discussion here. It's very simple. It's like basically dilute it and put it into the sea. For the case of separation, i.e. you're going to concentrate it first by potentially the electrolysis and fractionation method we discussed in a previous presentation. The depleted product is discharged into the sea by a pump. From the technical and regulatory viewpoints, there have been precedent cases in Japan and in the world. A set of estimated values of cost and duration is presented in the table too. So I bet you didn't know that somewhere in the world they've been dumping stuff into the sea. But there you go. So vapor release, the treated water will be directly vaporized by heating up to 1173 degrees Kelvin to 1273 degrees Kelvin. This is very clearly steam. Okay? The produced vapor gas is diluted with air and is released into the atmosphere through a stack. The stack height was estimated to 60 meters above ground level to assure the tritium concentration in the atmosphere is beyond the exclusion zone. So basically what they're saying here is if we can do vapor release, I'll say it straight away, I do not like the idea of vapor release, because vapor makes clouds and clouds precipitate through the water cycle, and everyone knows the water cycle from their primary school geography, right? So this is kind of like not bothering to pump it into the sea, type getting it into the sea, but potentially spreading it all over the land as well. The vapor release is technically getting around a legal construct that says at the boundary of the exclusion zone, this process will not raise the radiation exposure at the end of the boundary zone above a acceptable limit. Therefore, there's no scientific effect on people. But it goes up into the atmosphere, spreads around, maybe drifts across the Pacific, and then rains down on California and West Coast states, Washington. Maybe people have an opinion about that, but anyway. So the point is that the idea of putting vapor into the atmosphere, I just don't like it. I'll say it there. I don't like it. Anyway, so now the interesting thing is here. This is very valuable because this is what we are up against. This is the cost and duration of each option. So if you look at geosphere injection, with and without pre-treatment, if you have this is pumping it into the below the earth. If you actually dilute it and pump it, it's going to be very, very expensive. It's the most expensive option. I do not think, there is a cat's chance in the place underneath us, potentially, of this ever occurring, the geosphere injection. They don't even have a location for it. And if they did have, if they had a location and it's not on the site of the reactor, then they are going to have to ship this treated water somewhere. They're going to have to put it on a ship and ship it, or they're going to have to put it in, containers and put it onto lorries and ship it somewhere. I just don't think this is going to happen. It's just not practical. Plus, once you've got it under the ground, you need to look at it for 912 months potentially. And this is because of those. I think it's 29 point whatever years half-life for strontium and the 30.16 or whatever it is. They're both around about 30 years for both cesium and strontium. And so you have to monitor it for this long to understand what's going on. So this is not an option. And then the underground burial method, which I've not talked about, but this is essentially just like putting it into concrete and then burying it. This again is really rather expensive, but you don't have to do the treatment. But again, you have to monitor it, and because it's in concrete or whatever, it's even harder. So if you look at the hydrogen release here, they're saying either 60 to 100 billion yen. Vapor release, just forget that. I can't imagine anyone that thinks that this is a bad idea would think that this is a good idea. This is basically the same idea, and it's just a lot more expensive. So The reality is the discharge into the sea post dilution, and the reason you dilute it with seawater is that you want to have the amount that's coming out at a level that at the boundary of the exclusion zone, it's below the legal limit for discharging of radioactive material into the environment. They are saying 1.7 to 3.4 billion yen. That is basically insignificant compared to the other options. You can see why they want to go down this route. And what does that translate to in money we might have a understanding about? Well, if we take the upper limit, and let's face it, it's always going to cost the upper limit. That is our budget for whatever process you're having to compete with this. It's $30 million. That's it. That's what the money is on the table, right? Because they're saying that, and that's the 3.4 billion yen. If you're looking at hydrogen release, they're estimating it costs a vast amount more. You know, it's like 1 and a bit orders of magnitude bigger. It's a lot more expensive. Now, if you look at their hydrogen release down here, it says hydrogen release. The triated water would be electrolyzed into hydrogen and oxygen, and the produced hydrogen gas will be released. The exhaust stack height was estimated at 20 meters above ground level to assure the tritium concentration in the atmosphere is beyond the exclusion zone is less than 70 becquerels per centimeter cubed. The actual triated water contains chemical impurities. So here you have a second admission that there are chemical impurities in it, and these impurities would decrease the performance of the electrolysis cell. So where I am saying that if you had a very good electrolysis cell, at let's say 70%, 75% efficiency, that would very quickly, because of the chemical impurities, and one might assume that they are these other elements that haven't fully been got rid of, or some part of the ALPS process is leaving something in that water, that this is going to fur up and reduce the capability of the electrolyzer. So you might go from your super duper electrolyzer that's doing 70-75%, and it comes down to the level that the Amasa vibrator does, but it continues to drop because it's not self-cleaning itself. The fact that the Amasa vibrator system is shaking, it's going to be cleaning itself, plus potentially transmuting in a beneficial way and doing the electrolysis. So I think that actually our option would actually be dealing with this problem that they've identified. So we could work with electrolysis to produce a solution that deals with one of their main problems here. Also, the electrolysis cell should have quite large processing flow rates. Well, I had information from show that Amasa has built a 1 ton test unit. So this is a possible thing here. From the viewpoint of regulation, the hydrogen release must be carried out to assure permitted conditions, i.e. it doesn't scientifically affect humans, people, or rather that's what they say. But let's think about this. If you dump water vapor into the air, as I said, it forms clouds, it rains, it goes into the ecosystem. But if you put hydrogen into the air, or actually oxyhydrogen, the hydrogen will go up, it'll go up, it'll go up, it'll go up, and it'll go up into the upper atmosphere. It's not going to be the kind of environmental problem that the vapor release is. And so when you put that into consideration, discharge into the sea, whichever way you're looking at it, all that radioactive material, which does include some of that strontium and cesium, all of that is going to be causing long-term damage to the fisheries and so forth. Maybe not in a scientifically provable way, but it will change things. It is putting tritium into the food system, into the food chain. So if we look at what they are proposing for hydrogen release, no pre-treatment, 60 to 100 billion yen. Okay, so 60. I've got 100 billion yen here. We're talking 908 million. We've got 900. I think there was more money stolen in the recent handouts in various countries by people that weren't deserving of it than this is costing right here. It's literally less than $1 billion. And as far as I understood it, they're talking about somewhere between 250 and 750 billion dollars. This is a small price to pay compared to the $30 million, which puts it's just morally repugnant in my view to dump that into the sea. And as you can see, the reason you would be doing it is because it's basically cheap. That's it. It's just cheap. It's just cheap. So ask yourself, is a process, if we just are electrolyzing it and dumping the gases into the atmosphere, the hydrogen's just going to go into the upper atmosphere. It's not going to be an issue. Helium leaves our atmosphere, and helium's a lot heavier than hydrogen, so it's just going to go out of our atmosphere. The reality is the hydrogen in the atmosphere is extremely low concentration, extremely low. Just basically isn't there as a proportion. So this is going to leave anywhere that biology lives. And so a worst case scenario is if and I'll show this in my summary slide, if the transmutation doesn't work, you still have an electrolyzer which deals with one of the biggest problems they identified with electrolyzers. Okay? So the underground burial and so forth. So they're talking about the separation methods, and this is something similar to what we discussed with fractionation and so on. Anyway, so basically they haven't concluded anything. So I've got my summary slide, which I just want to point out here. So these are my the proposal options are. You can pre-treat with vibration. That is to say, you can have a Mars vibrator plate systems or vibration systems in all of the storage tanks all of the time. So they can be pre-accelerating the reduction in beta isotopes, strontium, cesium isotopes, and tritium in the water. So when I was with Roy Shinamaza, I imagine getting these vibration systems and just dropping them into the top of the tanks, and they just sit there and they vibrate, and they're made in such a way that they stir the water at the same time, so they're vibrating and stirring. So that's one thing. Then once you've done the pre-treatment with vibration, you then go into big versions like the 1-ton unit that he's apparently built. And you do vibration electrolysis, and this solves, in my view, the major problem with the electrolysis efficiency going down. It starts at a lower level, but it's robust, in my view. And what you get is high quality water gas, Amasa gas, from a robust device. So we know that Amasa water gas does transmutation, and it could be the case that we could use this in the reactor by having pipelines and use the gas directly to actually deal with radioactively contaminated material that's in the reactor itself. So you have this potential to actually fix the source of much of the contamination that's going to take 40 to 50 years, maybe, or more. And you might end up in a scenario where you are reducing the time to clean up of the site. But the first port of call is to get the tritium water under control. So vibration alone may assist the stabilization, especially with additive. Now, I will talk about the additives at a different time, but based on my understanding, I think you could add potassium hydroxide. The problem is that is corrosive, but potassium, as I identified, and then I found out that obviously Alexander Parkhomov had already said it in his book, that potassium could help accelerate the process. And so with the additive or after concentration, so as you're cycling this round and you are if you remember from the previous patent that we discussed, if you electrolyze triated water, you get less of the tritium than you do for the protium based water coming out. And you would imagine there's deuterated water in there as well. And so what you get left as the residue water from your electrolysis is higher and higher and higher concentrations of triated water. But of course it's in the vibrator the whole time. So it's kind of like where it needs to be prefixed before it becomes a gas. But you end up with the concentration. So it's actually doing the concentration process at the same time. So they're burning the gas in a mode to force coherence. So I'm saying against the block of calcium oxide or through a hole to create the tori. So by drilling holes and doing that. And actually, I told this before that Ken Shoulders found that he would create incredibly powerful EVOs by passing an EVO or an EVO generator through a capillary. And so, that this is, it's the fluid dynamics process that is going on that's force functioning the toroid to form, and that is forming the pinch and so forth. So I think that maybe going through a hole, this does mean that rather than using quarry tools, you might have to use a CNC drill to go and make a load of holes, and then the torches would line up with those in the system. And you would have to look at how long the calcium blocks last, but the idea is that this calcium carbonate source material is cheap as chips. It's just you literally put it on a container ship, and that is it. That is your material that you're interacting with. If it transmutes, done, great, fantastic, it's done, right? If it transmutes largely, like in Brown devices, then if it does a 1:100 ratio, like he observed in a few seconds once the flash occurs, but we're looking at creating a continuous coherent structure, then absolutely fantastic. And we have evidence to support that will potentially happen. But if it doesn't do it straight away, if it partially transmutes, then recycle, put it through, and not only it's dealing, as I'll reiterate this, it's not only trying to deal with the tritium. It could be dealing with any entrained cesium or strontium as well, and maybe you could use it to process the residual material that comes out of the electrolyzer. So if it partially transmutes, recycle, done after a number of cycles. If it does not transmute, you can use the heat for vapor release, which, I don't want to do that, but you could actually use the heat to do that cycle that you saw in the Huang reactor, where you use the heat to create water or steam that then goes through a double layered pipe, and on the backflow you have the water that you're going to put into the electrolyzer, and it's cavitating through there, and it's causing cavitation driven transmutation and stabilization of that going through the pipe. So you can actually use the heat in that way to do yet more cavitation through using the Huang technique. And then that goes into the electrolyzer itself. So you actually loop it round through that kind of process. And then if it does not transmute, you can use the heat for vapor release, or the water gas is released directly. So my second option is to release the gas so that it goes into the upper atmosphere, and it's not a problem for biology. So by doing this, using Amasa vibration systems, one, you have the potential to pre-treat with just straight vibrator plates in the tanks. Then you have the potential through vibration to do part of the transmutation before it's even done the electrolysis. The vibration electrolysis leads to higher quality Amasa gas, which we know does transmutation. So as this happens, the electrolysis happens, you'll get concentration of the tritium in the water in the electrolyzer. As you keep feeding in fresh stuff, you're going to get concentration. And so as the concentration goes up, the vibration efficacy might increase in reducing the tritium in the electrolyzer tank. The tank, the Amasa vibrator tank is resistant to the clogging up, as they've identified as a problem with normal electrolysis things. Then the burning the gas mode and force coherence, we can learn from the work of Ken Shoulders, through capillaries, through Anatoly Klimov, and from the observation of Slobodan Stankovic, who's on the team. And so that we have many chances to improve the formation of coherent matter, exotic vacuum objects. If it transmutes, done. If it partially transmutes, done. Run it through a number of cycles. If it does not transmute, you can do the vapor release, which I don't like. If it doesn't do that, you can release the gas directly. So we have many bites of the apple with the one kind of system to deliver one or more of the options. So it's kind of like the same installation can deliver one or more or a combination of the options. So in fact, if you wanted to increase the rate of processing, you would kind of like maybe just skip straight to releasing the gas. If you wanted to deal with the waste properly, and it might be that before it's overly concentrated, you release some as water gas, but when it is concentrated, you then actually burn it and do the transmutation. And you might find a trade-off between those cases. So that's kind of what I'm thinking of there. That's where we are in our process. We have this material that should be with us that we can run testing on. I already have some small amount of deuterium. I need to check with Slobodan on how much he needs, or how little he can put in a tank, so that we can have a high level of concentration, and whether we need to buy any more deuterium to work with. And so that's basically it. So have you got any questions, any suggestions? In this case, you can suggest under the video. I've not got a blog for this. It was just an interim posting. So I'm just going to quickly look through and see if you've got any questions here. Okay. Yeah, so Slobodan is saying one of my suggestions was that Japan export the triated water to who want to use it with our solution. Yeah, the triated water, because of their obvious preference to use the dumping in the sea, it's worth about how should we put this? It's worth about $15 million to them. Like, I guess if you were to offer to buy it off them for $15 million, they'd say, like, show us your money. Now, if you had a process, the problem is you need the triated water to show that you have a process that can deliver some benefit. Okay, I'm just looking at your comments. Yeah, the Tesla turbine and these kind of devices, we have a massive flow rate. The technology has to be super duper simple. It has to be really simple. And the reality is the Amasa vibration electrolyzer system is really simple. I think the biggest barrier really is the fact that it's so cheap for them to dump it into the sea. So you've got your I guess your biggest support that you can get is from those like you and I believe, that don't want that to be put into the sea and to go into the food chain, even if it's not going to be able to be scientifically proven that it's going to harm people. Yeah, I mean, a range of different materials should be tried, and that's what you would do when you had enough materials. Sorry, when you had enough tritium water. I mean, we kind of really need just like a 4 liters or 5 liters of tritium water, and yeah, Bob Kenter, zero discharge. That would be my goal. In the working document, they are asking for a 1 to 1,000 target. In this document I discussed, it was 1 to 100, and they've only achieved 1 to 10. So they're like 2 orders of magnitude away from where they want to be. I think when you get to 1 to 1,000, then people, because actually tritium, as I showed in that pattern from a previous presentation, tritium itself, tritium water, is relatively easy to store. And if you've got 1,000th of the volume, you've obviously got 1,000 tons, not 1,000,000 tons. You know, there's still 1,000 tons, so let's get rid of the 1,000 tons. That's what you want to see. You want to get rid of that 1,000 ton. Yeah, I mean, that is the thing. It's like, what is the hardness of the water? And they are specifically saying that normal electrolyzers do get clogged up with mineral content in the water. Okay, that is where I think the Amasa vibration system really has a huge advantage. Yeah, centrifuges separating something that is 1 neutron heavier or 2 neutrons heavier, it's just not really very good process, to be honest. You're better off, like, so the methods that are, is the electrolysis method. You get 3 times the amount of protium-based hydrogen out than tritium water if you in electrolysis, and by fractionating by heat, the same way that they produce heavy water. This isn't something that you could easily do, in my view, with centrifuges, and that's not the case because it would have been a suggestion when they had several years to consider this. They are in the nuclear business. Then most nuclear reactors started their life off desperately trying to make plutonium, and to make a nuclear reactor work, you need to create. To make plutonium, you need, or rather, to get the uranium you need for a nuclear reactor, you need to do uranium enrichment, and it does use those kind of processes. So that would have been a thing that they thought about. So I don't think, Bob, that centrifuge is going to be a practical for the 50 to 150 tons of triated water that they produce a day. So yes, Slobodan saying it would be great to have some water to test this solution. That is something that we've got to work on in parallel. But given the fact, I don't know whether you were here at the beginning of the presentation, but I was talking about the fact that Amasa, it is his understanding that when he did test triated water, that it acted faster than deuterated water, and that acted faster than protium-based water. And so the Parkhomov MFMP reaction tables suggest that you get a higher yield out. What does a higher yield means? It means that it's going into a smaller box, which means it's more likely in a coherent matter compressive technology, implosive technology, and that's, I believe, what you're going to get with cavitation. And so coherent matter, and so all of the dots line up. So I think we can do a reasonable analog of it by using deuterated water and comparing that. The problem we're going to have, particularly with calcium, is that some of the mass analysis techniques use argon in them, and argon has around about the same mass as isotopes of calcium. So you get a challenge there with measuring different isotope for calcium. Civilian Space Agency, you're saying, yeah, just dump it in the ocean. We have an opportunity here. Firstly, if you allow for the dumping into the ocean, we're not just talking about the 1.1 million tons now. We're still producing, let's say, 100 or 150 tons a day. What you would be doing is sanctioning the continual release for a very, very long time, like 50 years. This is just dealing with the problem you got now. This problem has to have a long-term solution, right? Moreover, if we can demonstrate that it really does, if it doesn't work, if it does not work, then fine. You know, we tried our best, but we must try. And if it does work, we have a solution to deal with this problem in the future, right? And is that not worth the price of admission, you know? So Gordon Doherty says, what next? Load it into a rocket and fire it into the sun. Well, actually, Ken Shoulder says you could use EVOs, put anything in there that you wanted to get rid of, like plutonium-239, and then accelerate that and fire it off into space. And yes, fire it into the sun. He actually suggested that as a way of getting rid of radioactive waste. This is a lot of material, and it's not really a practical way to do that. Yeah, tritium only goes one way, headed out into space if released. I agree. That is why the overall proposal that I'm putting forward here today, it has these multiple chances of winning, if you know what I mean. So, you know, if it doesn't work, you know, if it does not transmute, the same system can reliably electrolyze the water, and rather than just releasing the hydrogen, you release the water gas directly, and it'll just float up. The hydrogen component will float up. There is an issue with water gas. You know, maybe you would have to make a variation of it, because some water gas is heavier than air. So you would have to account for that. Civilian Space Agency, looking way much into this. When will you get back to John Hutchison and the Hutchison effect? When I realized that Lena most easily destroys nucleons, I thought, you know, you're going to have a problem creating excess heat and energy systems with this, because as soon as you start upping the output, you're going to get destruction of your reactor. And this is what you see across the board. Barkamov saw it. Most recently, in the last presentation, Huang saw it. You know, they're only getting a 2.55 COP, and they want to go to 10. But, you know, they're already seeing the destruction of their reactor very, very quickly, potentially. And so it's because of how it works. So I thought, what is the practical use for this technology immediately that would allow us to learn more about it and get it on the map and proven, and so that we understand it properly, and there's more minds looking at it seriously and accepting it. And that would be to fix Fukushima, Daiichi, Chernobyl, and Enewetak Atoll. And that is basically where I was at the beginning of 2017. When I was first put in contact with John Hutchison, he said that he's not really interested in his old effector more. He really wants to fix Fukushima. And basically we were like that because we both had the same goal. So in fact, the only reason I was able to visit John Hutchison is because we had that common interest. And it was a common interest that I had signalled well before I had an opportunity to go and meet him. And so one follows the other. Freezing it and trucking it is a good method to to actually ship it. Yes. I'm talking about good vibrations. Gordon Docherty's song choice of the day. No, you're saying is a portion of the chemical contamination salt. No, they have a desalination unit. That is part of their processing. So if you go to the paper, after they do the cesium adsorption, they then put it into desalination. So it removes the salt. Now, if you are vibrating this, you might want the salt in there. That might assist in the transmutation of the radioactive isotopes. Then again, it might not. So anyway, the point is it does remove the salt. So thank you for that question, David. Actually, yes, ultrasonic, but I believe any sound will have resonant nodes, and it's at one or other of the nodes, as we've talked about in the past, that you get the conditions for far from equilibrium, which produces this kind of coherent state. And so, bizarrely, and so if you have higher frequency, you get more nodes. And so there is more locations because you're working with things that are atoms, and they're quite small. So a lot of nodes is good. So ultrasonics is better. And in the case of Suhas Ralkar, in his reactor, he was using megahertz. Civilian Space Agency, they've got all the heavy elements out of it. They've got a process to remove basically everything, all bar trace of cesium isotopes and strontium. It's just the tritium they're dealing with. So potassium hydroxide, no, yeah, I mean, potassium hydroxide is not corrosive. Yeah, well, maybe not if you don't put it in aluminium. But anyway, yeah, I get what you're saying. I would use potassium hydroxide as an additive, as I'm suggesting there in point 3. And actually, that will feature in one of the other presentations I will do this week. Civilian Space Agency, I proved on day 1 visiting Roisin Amasa that his Amasa vibrator system, from which the electrolyzer, the Amasa gas, has its heritage, that does ultrasonics. It's a mode that is produced harmonic. Yes, David, it's to use these techniques for a form of LENR to decompose the tritium into stable elements. Yes, that is essentially it. Either to pass the neutrons onto, say, calcium, so you've got most calcium is calcium-40, and pass the neutrons so that you either get deuterium formed or you get deuterium and calcium-41, or you get protium and calcium-42, or that you actually take a proton away from calcium-40 and you end up with potassium-39, which is the most abundant form of potassium, and you get helium coming off. And that is what would seem to be, from the earlier calculations from the reactions calculator, quite likely outcome. Okay, so Axel is asking, will the pre-treatment Amasa vibrator be upscaled? I originally thought that when he was doing his vibration treatment in 2012, that it was just vibration. But I think I'm right in saying that there was electrolysis going on as well. Whatever... he was able to remove 1 half-life in 15 days and 2 half-lives in 30 days. So what you're actually looking at there is, if you've got a body of water and you remove 1 half-life, you've effectively reduced that. It's 1 half of the volume at the same radiation level, if you know what I mean. You've removed 50% of the radioactive isotope. So in 1 month, you've removed 75% of the radioactive isotope, tritium. And so you can imagine you get a law of diminishing returns, but you are accelerating time. And so the idea of having vibration in the tanks is that is pre-processing it, so that by the time you get to work with the material, it's actually a much lower level of emissions. So, Gordon, as to killing everyone, burning fossil fuels is doing just yet. Yeah. If we can deal, and part of my motivation is if we can deal with the problems of an accident, and we can deal with the nuclear fissile waste using a Mars gas or a Mars vibration or HHO or water gases in general, then you are able to use nuclear in a way that you can put it in many more places, because it has a much better safety profile than actually its quite good safety profile. I mean, obviously not in Fukushima Daiichi district, but it generally, for the amount of people it kills, and here we're back to the people argument. But people working in coal mines, there's quite a lot of deaths. People working in the oil industry, well, there's quite a lot of deaths. How many people do you know that have died, not personally, but have you heard about, that died in nuclear accidents? Well, obviously there's some at Chernobyl, and there are some that probably died early in Fukushima Daiichi. But I know that a lot of old people went in and volunteered their twilight years heroically to deal with that initially when the radiation level was at its highest level. But people are dying every single day in the oil and gas industry, huge numbers of people all over the world. Even if you just look at the people in Nigeria stealing oil from an oil pipeline, there are scores of people dying every year just from that. And so, when it comes down to the people argument, the hydrocarbon industry is quite deathly. Civilian Space Agency, as I said, it's very open about it. They are dumping the sump water into the ocean, where in between the ice wells. So that is what they're doing already. That's actually a very good and interesting point, Shanjak. I'm not quite sure how to say your name, but potentially that the heavier isotope might get caught into the EZ zone around the electrode. So that is actually a very interesting point. I think it's worth researching. That's a very, very good contribution. Thank you. Okay, Civilian Space Agency. You seem to be repeating yourself quite a bit. We are talking about dealing with the tritium water. Okay, if it was just a matter of centrifuging, they would have done it. The industry, as you correctly know, use centrifuges all of the time, and it's used in many different material processing technologies. But you generally have a good separation between the masses. The reason they spend so long separating uranium isotopes or plutonium is because you need a specific isotope to produce the nuclear critical mass, either for normal fission or for the N bomb. And so the goal is worth spending a very vast amount of time and a long time doing the centrifugal processing. I imagine that trying to separate by centrifugal in this process would just be unimaginably expensive. Unimaginably expensive. And, you know, water moves like water as well. I mean, you know, it just moves like water, doesn't it? So, I mean, you could use the old Schallberger, the dense part of the water is in the center, and so forth. And, you know, vortex itself would end up with the dense part in there. And so you could consider those techniques, like the feed from the tanks could preferentially be the water that's extracted from the center of a vortex coming out, whatever. You might get a higher concentration, but the known techniques are fractionation by temperature and by the fact that electrolysis preferentially does the lighter isotopes. Okay, we're only dealing with the tritium water here. We know there's a lot of problems at Fukushima. And actually what I'm suggesting is that potentially the gas could be used to deal with some of those other problems. But first we have to get an audience and an opportunity to test a technology that may or may not work. The likelihood is, and the evidence is, through history, from Yul Brown and other tests for many decades, that it has a good chance of working. It certainly seems to have done in the past. And Amasa has a technology that's quite robust. And so we're dealing with, you know, let's not try and bite off more than we can chew. And at the moment, we haven't got anything to chew, even on this basis. Okay, Axel is asking, in a large tank, would the vibrator plates needed to be made larger than is done in the Amasa's hardware? Actually, you don't need to, but I have seen in his factory very, very large vibrator plates. I mean, really, really large vibrator plates. So it scales. Yeah, there's the John Watson is correct about the air quality due to coal and gas. Whether you like it or not, there are countries around the world, like I think it's Finland and obviously China. And when I was in India, in Tamil Nadu, they were installing two 1 terawatt reactors, and they had a deal with the Russians to install another 5 2 1 terawatt reactors. So that was another 10 terawatts of nuclear power going into India, and that is a lot of energy delivered via nuclear power. So we should try and find a solution, because what you are seeing in that paper from May 2020 is there is no solution to this problem. There's no solution to this problem other than dumping it in the sea, which is dilution is a solution to pollution. It's not really a solution. It's not really a solution. It's a cheap option, and not scientifically able to prove that it will affect people. Okay, what I'm trying to work towards with Slobodan and with John Hutchison and with Alexander Parkhomov and so forth, is a solution, an actual solution to the radioactive isotopes. And if it doesn't work, I don't care. At least we tried. So David Boutelier, you said Boutelier. Sorry, I've got your name right now. The resonant nodes would need to have the amplitude large enough to have a significant effect. However, it's funny that you said the resonant nodes have to have sufficient amplitude to have. If they're resonant and the damping is not too high, then they will always achieve the amplification. What you actually want is resonance and low damping. If you've got resonance, you don't have to have initially much amplitude at all, because you will, assuming there isn't too much damping, you will always achieve the amplitude you need. Certainly LED lasers might help, Felix Audet. It might be that lasers could support the process. And WP for Truth, yes, Stanley Meyer used lasers. And what do we know about lasers? They will cause coherence. That was in that patent, which is now from whenever it was, one of the ones I recently discussed. He was using lasers. Kathy B, I believe that this has a very good shot at being a solution. We already know 100% certainty that a Mars gas transmutes metals, and when it transmutes metals, it transmutes them typically to rock forming, biologically available elements that you can eat, and they're good for you. Right? We know that unstable elements like to become stable. That's what they do. Stable elements don't tend to just sit there and spontaneously become unstable. That's not what life does. It goes from instability to stability. And John Hutchison says, you know, my technology is kind of like a time machine. Well, it isn't. It would appear like a time machine because, for instance, you use cesium-137 and rubidium-87, which are radioisotopes, beta radioisotopes. You use those for radio nuclear clocks. These are clocks that are highly accurate because the decay rate is supposed to be very, very precisely known, and so you get a very precisely measuring of time. But actually, Xu and Zhu in between 1988 and 1999 showed that in three-body alignments something occurs, which he didn't know at the time, but we know that during three-body alignments there is a change in the flux of cosmogenic relic neutrinos. These clocks changed their time depending on whether they were under the eclipse or outside of the eclipse. And he also went into the historical data published by American nuclear clocks, where there were eclipses and the same pattern was occurring. So what this shows that something was causing that process. And he also found that the spectral lines of elements changes during three-body alignments, and that should never happen. And that goes back into the argument that I was talking about last night about Leonid Uritskev saying that the magnetic Loschek magnetic monopoles, which he argues is a magnetically excited neutrino or neutrino condensate, that was going into the air above Chernobyl, and that was interacting with the gases, predominantly obviously 78% of air is nitrogen 14, and 20 or something percent, 21% or nearly 21%, 20 to 21% is oxygen. So it's interacting with those gases. Likely it's interacting with the oxygen in the air for the reasons that it's paramagnetic, and that then when that is ionized by actual beta emissions or gamma emissions from decaying particles that were coming out of the reactor, the ionization is causing electrons to go up to a higher energy level, and they're coming back. But because of the magnetically excited cold neutrino condensates, these structures in the gas, it was producing non-natural glow, which was observed by literally hundreds of people, as I understand it, and is probably the only thing that's semi-accurate about the HBO documentary. One thing that I can really stand behind. Yeah, you got to turn it up. You're right, really. Okay, well, I've got to be up in the morning because I'm going to go and visit SciTech and try and get some access to their EDS, and I think that's and they also have some other tools there which will be very, very valuable. They have a I think it's a 5-meter high transmission electron microscope, so that can actually look down to the atom level. They also have well, they basically have a wide selection of materials there. So so I'm going to say thank you. If you have any other suggestions, I think the proposal that I'm suggesting here means that one of the biggest complaints that they had was that electrolysis has this problem with getting furred up. I don't think that's a problem with Amasa. I think that's a huge win. I think the fact that Amasa is Japanese, it's a huge win. I think that because we have proved that Amasa gas transmutes matter, and it transmutes matter to stable elements, that's a huge win. The fact that that pattern is the exact same pattern that's observed by another Japanese nuclear researcher that spent his life trying to work out how to deal with radioactive waste, that is Takaaki Matsumoto, and the same effect occurs between his experiments and Amasa gas treated metals. That is a huge win, and the fact that we have another person on the team that's observed the same production of elements as was observed, both Amasa and he has observed, and the same patterns of the way that these things are observed, and that is Slobodan Stankovic. I think that is a huge win, and I think that the fact that this was proven, and you can see the videos of people giving testimony that Brown's gas does this, and it also remediates other nuclear waste, I think that is a huge win. I think we've got a strong case to make, and I think that at the very least the process can lead to, at worst, releasing of hydrogen gas from the electrolyzers, where there just be a slight modification so that you just don't get the oxyhydrogen or water gas. You get straight hydrogen, in this case the isotope tritium released. So there's multiple ways that we can deliver various versions of the options which are not dumping vapor into the biosphere and not dumping liquid into the ocean, which for me are the two most likely ones to cause harm to the biosphere, and we want to, I think, avoid those at all cost. So thank you very, very much for your time, and I will maybe see you tomorrow, or it might be Thursday, and I have this real treat for you. It is I'm going to give you a hint. It is to do with coherence. It is to do with coherence, and I think if you have access to Alexander Parkhomov's Space Earth Human, I would like you to look in there to see why you think you can get coherence accelerated with his understanding, which I don't believe he has said, maybe not even thought of. But go back to the various presentations I've done recently and in the last couple of months on coherence, and refresh your memory. because the things that drive coherence, there's one very, very, very important thing that all of those processes are trying to achieve, and then cross-correlate that with Space Earth Humans findings, and I think you will. I'd love for someone to get it. I've obviously been putting hints out for a long time, but I think I'll probably either do that tomorrow or Thursday. So thank you very much, and I will see you in the next video. Good night.